Welcome back. I'm Lisa Blackburn. This is my YouTube channel where I talk about everything I want to, science and math. And today we are continuing the notes for Unit 5 on chemical reactions. So this is part 3 of that video. So join us, get out your notes. You can, if you're in my East Paulding High kids, you can print out the notes from Canvas. So go to Canvas and you can print out the notes if you're stuck. If you're stuck at home and so sad you can't be with us. All right, so if you look in your notes, we are at this point right here that says, what information is in an equation? So there's a lot, I showed you that the equation is like a recipe. And they have to really condense the information because they're writing a whole recipe as one sentence. And you know, think about cookbooks. They usually do a whole page for a recipe. And we're trying to get everything in this one sentence. So we have to use a lot of symbolism. Okay, so the first thing is the equations. You can think of them as instructions. So that's our fill in the blank there. Equations as instructions. Now, one of the things that can be written in an equation, and it's not always, usually in fact it's not, but one of the things that can be written in it is the energy changes. Do you remember what the symbol for change is? Triangle. So these are our energy changes, and here we have the energy written as a product, and here we have it written as a reactant. One of these gives off heat, the other one takes it in. One is exothermic, because remember, exothermic sounds like exit. I'm walking out of the room, I'm exiting, I'm heat, and I'm exiting. So which of these two do you think is endothermic, and which do you think is exothermic? You're right, the top one is exothermic, because see, the energy is leaving. So the bottom one is endothermic. It's going into. All right, so one of those symbols that we use is triangle H to mean that has energy changes. And this is a little bit confusing, but it's just the way the symbolism is if they write the heat underneath the equation, just as sort of like not as part of the equation, but underneath to tell you what's going on. If it's negative, it's endothermic, and positive is exothermic. So kind of makes sense. Because you're positively giving off heat, you're negative, you're sucking in the heat, you have a negative balance of heat and you're sucking it in. Can you kind of get that in your head? All right, the next one, reaction conditions in equations. Sometimes reactions will indicate the state of matter. You know what the state of matter is? What is the state of matter? Solid, liquid, gas. That should have been something you learned in science class in elementary school, the states of matter. Did you learn that?
Yeah, and plasma, right?
And plasma, but we don't usually deal with plasma in the chemistry classroom that much. All right, so reactions will tell you the state of matter. Because like it'll say, you need a chemical. Well, do I need it as a liquid or do I need it as a gas? How do I need it? So here's our match reaction written down. So this is what I was doing when I lit that match. And you see these little S's in parentheses. That's not sulfur, that's solid. You had my solid chemicals and I put them together and I was able to have that reaction and it was exothermic, okay? So we're gonna go through, and these are all little things that could give us, tell us more information on reaction. So I already told you what little S in parentheses means. What is it? Solid. What do you think little L in parentheses mean? Liquid. Y'all are brilliant. Yep, gas. Yes.
What?
Is aqueous, which is like aqua. That means you put it in water, right? So aqueous, this is, you want to put it in water. I spell it aqueous right? I better look before I write it on the board wrong. Aqueous. Yeah, it just seemed like too many vowels. Once you get 4 vowels in a row, you start questioning yourself.
Wait, what is it? AQ?
Aqueous. Aqueous.
Oh my gosh.
It's got a lot of vowels there. Aqueous. Okay, here I have a C with a little circle up top. What do you think that one is? It's Celsius, and how this would be is it would have a number written with it, and it means that you have to do this reaction at a certain temperature. So it would have, it's usually Celsius, sometimes Kelvin, but it means that it's a certain temperature. And big T is the abbreviation for temperature. So a certain, you can write out temperature if you have room or something. Okay, CR, any guess for that one? Here's our hint over here. Let's see.
Crystal?
Crystal, means you need it in a crystal form. Crystal. So like, there's a lot of chemicals in the stockroom that I have, and I can have them powdered, or I can have them in crystals, and you have to get the right one. If you get the wrong one, it won't work. Now, I told you this one yesterday. Do you remember what an arrow down stands for? A solid. It means that it's good. Usually it means you're pouring 2 liquids together, and it is going to form a solid. So this would be in the products. So solid forms. My pen, it just writes what wants. Okay, arrow up. I told you this one yesterday also. What is it? It means it's going to be a gas that forms. So that means you're going to get bubbles. Arrow over. I told you this one yesterday. What does it mean? Over here, what do these arrows mean?
Oh, the product?
It's like, it's what is it gonna make? And how we say that is yields. But you can think of it sort of like it equals. What does it yield? Now, PT is an element. Which element is it? Platinum. And it doesn't have to be platinum. It can be any element, but sometimes you have to add something to it to make it go. It's called a catalyst. Did y'all learn about catalyst in biology? Yes, because you learned that enzymes are catalysts in your body. They'll get chemicals together. They don't participate in the reaction. They're like a matchmaker that'll go get the chemicals and put them together. Remember that from your biology class? So sometimes you have to put another chemical in there to make it go, and a lot of times it's platinum. So that's why I put it on there. But it's called a catalyst. Come on. I feel like I need to encourage the pen. Catalyst. Now, that video I made you watch, did y'all notice how he said catalyst? The guy with the dreads? Did you notice he said catalysis? Never heard anybody call it a catalysis. And I've been to about 5 colleges. I've had many, many professors, and none of them said catalysis. I'm like, where's that guy from? That's weird. Maybe he's from an island or something. Can you see him being from an island? They say catalysis, I can too. All right, so I shouldn't make fun of his pronunciation. He might make fun of my southern pronunciations of some of these. All right, and if the arrow goes, sometimes you can have an arrow going 2 ways. And that means that the reaction is reversible, that you can make it go the other way too. And you're actually familiar with this with, what am I gesturing to here? Your phone. You know how you have to recharge it? Your phone has a battery. A battery is full of a chemical. The chemical reacts and produces electricity. If you run the electricity through it backwards, it recharges it and it reforms the reactants until finally it doesn't work anymore. And then your battery life is over. And it is a very sad day, right? when it quits charging. My DS, sadly, my cute pink DS that I played Animal Crossing on, the battery betrayed me and it won't charge anymore. And my calculator, my cute pink calculator is about to get where it won't recharge either. So that you love them until suddenly they don't work anyway. Also, an arrow two ways can stand for equilibrium. Which means that it is a reaction that can go two ways, but it will finally settle to where the reactants equal the products. And we're going to do a whole unit on this, so don't worry about it. Okay, what do you think a triangle stands for? Change in heat. So if it's just sometimes trying to be cool, they won't bother with the writing the word heat. They'll just put a triangle, and that means you have to heat it up to make it go. And then heat is also, if it says the word heat, it means you heat it up. KPA, that stands for kilopascals. What are you doing to Pascal? You're not killing him. It's a pressure unit. Sometimes you have to put a reaction under pressure. And there are other pressure units, millimeters of mercury and things like that, but any of them mean that you have to put under pressure. What do you think you have to do with it with a little e? We saw our guy do it in Adam's Ring of Truth. He did it to water.
Oh, electricity.
It's electricity. It means you have to shock it. It means you have to shock it. It needs a little electricity. Like bringing Frankenstein to life. Oh, right. So he would have a little E on his reaction. All right, quantitative relationships. What does that word quantitative mean? What does quant mean?
Energy?
No. Quantity means how much.
An amount?
Amount. Qualitative is what is the qualities of it. So in chemistry, we do qualitative analysis, figuring out its color, its properties. But we also do quantitative analysis that tells us how much we're making. Okay? So quantitative relationships. Equations reveal the number of formula units involved. For example, here's a reaction where we have sugar plus oxygen. So if you had some Cheerios this morning or some Captain Crunch, some sort of sugary cereal, then you are doing this reaction right now in your body. You ate your sugar, you're breathing in your oxygen, and then you are going to get the energy out of it, and then you're going to breathe out some, what are you breathing out? Carbon dioxide, and do you feel it in your breath? Some water there too, feel the moisture in your breath? And energy. So this is burning food. Now you don't have a little flame in you. I know it's shocking, like a dragon. Instead, what burns this is we chemically burn it. We use chemicals, acids, to burn the food up. So these numbers in the balanced equation are going to tell us the coefficients. The numbers in front are called the coefficients. The coefficients tell you the relative number of formula units. So you look at the number in front and it tells you the number of moles. Do you remember what a mole is? We learned it like our first unit.
Yeah, it's like
It's like what?
the amount of like how much one atom or one like element is, right? Like how many?
You're getting there. What is it like?
6 milliliters.
I'm pointing my foot. Or
An egg.
it's like a dozen or a pair.
Oh.
It's an amount we measure chemicals in. So I was pointing to my pair of socks or a dozen eggs. How we get chemicals is in moles. And 1 mole is Avogadro's number, 6.022 times 10, we go on with that. And it is what you measure it out in grams. And that's how much a mole is off the periodic table. You remember that now? So we're going to talk about that here. So looking here, the coefficient tells you how many moles you put in the reaction. What's understood to be here? What's understood to be right there? A 1. So we have 1 mole of sugar, 6 moles of oxygen, 6 moles of carbon dioxide, and 6 moles of water. Okay? Now, let me find my little paper here. I moved it around. There we go. All right. So molecules, now who remembers what is Avogadro's numbers? 6.02 times 10 to the what? What? Starts with a 20. 23. 6.02 times 10 to the 23rd power. So we have one of these. If we with this one, to get the total number of atoms, you would multiply 6 times it. So I don't have room for it. So I'm going to say 6 times Avogadro's number. Y'all know what that means? This one would also be 6 times Avogadro's number. 6 times Avogadro's number, which is that. That is Avogadro's number. Okay? Now, how do we change this? I don't count atoms, 1, 2, 3 for a reaction. Remember, I used the periodic table. So how do I get from molecules or moles to how much to put in my recipe using the periodic table? What part of the periodic table do I look at? You only have 2 numbers. Do you think it's the mass or the number? It's the mass, because the mass is how much 1 mole weighs in grams. So if I need 1 mole of carbon, I go get 12 grams of it. If I need 1 mole of oxygen, I go get 16 grams of it. So I need 1 mole of this. I have to add up all of those masses. So I'm going to do it over here. So carbon, I'm going to write it like this. Carbon, hydrogen, oxygen. Carbon weighs 12. We're rounding off to big numbers. Hydrogen weighs 1 and oxygen weighs 16. How many carbons do I have? See that little number in subscript? 6. How many hydrogens do I have? 12. How many oxygens do I have?
6.
I have 6. So I'll do my multiplying on my calculator, so you're going to remember your calculator for this test. And 6 times 12 is 72. Y'all want me to sing the song? It started with a 0, 12, 24, 36, 48, 60, 72, 84. So it's 72. Do y'all have little math songs for all the multiplication tables too? I do. I'll sing them all for you some other time. If you were taking math from me, I would sing them all for you. And I have hand claps for them too. But we're not there right now. All right. So 12 times 1 is 12. And 16 times 6, I don't have a song for the 16 tables. I'd have to do it on my calculator, but it's 96. And then you add them all up, and it's 180. So this is an important math problem you need to know how to do. So the mass in grams of this one is 180. I'm going to go ahead and tell you the answers to these. And, yeah. 180. Okay, so oxygen is 16. 2 times 16 is 32. Carbon dioxide is 12 plus 32. And it can do that in your head. It's 44. And water is 2 plus 16, which is 18. So now to get the total mass of each one, I multiply it by the coefficient. And that's how I know how much to go get out of the stockroom. So 180 times 1 is 180. 32 times 6 is 192.
Wait.
You multiply the molar mass of the chemical times the coefficient.
Oh, okay.
Okay? So it's 32 times 6 because of that 6. You multiply these two.
Where'd you get the 32?
I did 16 times 2 because there are 2 oxygens there because of the subscript.
Oh, okay.
Does that make sense
And
now?
then for
So we're going to do 44 times 6, 264. And we're going to do 18 times 6, which is 108. And if you understand this, you understand a very big concept in chemistry.
So the mass and gram was just the individual
For one,
for one of them.
but this one I had 1, but this one I had 6. And that's why we have to balance the chemical equations.
Wait,
So we know how many atoms we have, how many molecules.
why? Okay, so this. Okay, so like for the 32, so it's 6 up like oxygen. Wait, so why is 32 is not? Oh, okay. You don't multiply the 6 into the last column.
Yeah.
Okay, that makes sense. I understand now.
Anybody else? All right. So the balanced equations show you the proportions. If we had 2 molecules of glucose, that's our sugar, how many molecules would you have? So let's see what I want here. Oh, how many molecules of water would you have? So if I doubled it and had 2 of glucose, I have to double the water. So how much water would I have? If 1 makes 6, how many would 2 make? 12. All right. So the relative amounts can be expressed in moles. It's the coefficients that tell you the relative amounts. It is a ratio that can be determined. So if we are doing the glucose C6H12O6 to water, we can write that as a ratio in different ways. Do y'all remember this from math class? Learning that you can write ratios different ways. You can write it 1.6, that means 1 to 6. 1/6, that means 1 to 6. Or you can write out 1PO6, that means 1 to 6. It's a ratio. How do y'all feel about that? All right. Okay, but these ratios have to be expressed in whole numbers. And this is the products or the reactants. Let's see how I'll write that though. I'm going to put it in the ratio. Whatever you're looking at, you look at the coefficients and it's in your ratio and it needs to be whole numbers. That's what that means. All right, let's move on up. Y'all ready to move up? Okay, so back to energy. It's usually expressed in amounts per mole and given with the reaction. So right here, this is giving off 2,870 kilojoules per mole of glucose. For every 1 mole of glucose that you burn, this is how much energy you give off. Let's see. So negative means that it's given off, that it's hot. And if you had 24 moles of water produced, how much energy would be formed? Well, you look at your water here, and you have 6. So our ratio is 1 to 6. Now, there's a couple of ways we can do this. One way we could do it is that it's 24 moles of water, and we know that there's 6 produced each time you do this reaction with 1 mole of sugar. We could divide it. We could say 24 divided by 6 equals 4. And if 1 is 2870, but we have 4 times as amount, we could multiply it and we could get the answer, which is negative 11 480 kilojoules. Now, but there's another way to look at it also. You can set up a ratio, and you can say 1 is to 6 as X is to 24 to find that relationship. You cross multiply and solve for X, which this one's pretty easy because it's a 1. So 1 times 24 is 24 equals 6X. How do we solve for X? How do we get it by itself? By doing the opposite, right. So 6 is being multiplied by an X is being multiplied by a 6, so the opposite is to divide by 6. And what you do to one side in algebra, you do to the other side. You can do anything you want as long as you do it to both sides of the equals. So these cancel out, and we have that X equals 4. So we knew our factor that we need to multiply by was 4.
How did you get that crazy complicated decimal number?
This number?
No, the one at the 11.4.
Oh, it's not a point, it's a comma.
Oh.
It's 11,000. I multiplied 4 times that.
Oh, okay.
So we're going to do this times 4.
Oh, and that's, okay.
And that's how we got the answer. How do we feel? You're doing pretty good considering you're having to think about math at 9:15 in the morning. Very good. All right. Now, how can reactions be used? Why would we want a chemical reaction? Why do we want some chemical reactions? Like this. I paid for a whole box of chemical reactions. The whole value of this thing is the chemical reaction. Why did I pay money for this box of chemical reactions?
You have heat and light.
Heat and light. So the reason I would want it would be the products or the energy. And with the match, what I really want is the energy. I don't really want the burnt up match. In fact, I threw it away, and I will throw this one away too. Okay? Now, why would you not want a reaction? It can be dangerous. What can be dangerous about it? The products or the energy. So it's the same thing. So we do a lot in chemistry of making products and energy we want, and we also do a lot of making products and energy we don't want. Things that we don't want to have. We don't want pollution, so we put catalytic converters in our car. That's a chemical reaction. So now, there are 5 reaction types, and this is what was in your worksheets that you skipped, and I told you yesterday you were supposed to do these 4 pages, but to skip the part about the reaction types because you didn't know it yet. Now's the time you get to know it. So what I did last year in the notes is I listed the 5 types here so that y'all would really pay attention to it. But you're saying the same thing twice, and I don't like saying the same thing twice. So what I want you to do is what I did in my notes. Do you see my pink? I highlighted the 5 types. So at the end, you don't have to use pink. You can use whatever. But at the end, make sure you highlight the 5 reaction types so that you can memorize these. We're going to have a pop quiz on it. We're going to have it on the test. The main thing on the test, I mean, we are just about at the end of the notes. You can tell it's going to be balancing equations, doing a little math, figuring out the reaction types. So this is and knowing the evidences of a chemical reaction. So this should be, as long as you understand balancing chemical equations, you should do good on this test. So just make sure you do. All right, so here are our 5 reaction types. I'm going to roll this up. Okay, the first one is called synthesis. Okay, and how we're going to remember these is, I know we've already passed February, but it's going to be love and romance is how we're going to learn these. So for synthesis, I want you to draw a little heart by it. Do you already have a heart on yours? No, okay, draw a heart. So compounds are made in the synthesis reaction. So here we had a lonely hydrogen looking for love and a lonely oxygen looking for love. And now they are together in one beautiful water molecule. Getting together is synthesis. So that's the first reaction type. Got it in your head? Synthesis, love. Now, let's be real. If couples get together, what else can they do? Break up. So our next one is decomposition, and I want you to draw a broken heart. Oh, so sad. And we're going to get down to that. So we're going to go ahead and write this down. Compounds are broken. We're going to skip 2 for just a second. Compounds are broken down in a decomposition reaction. And that decomposition is what actually happens when you decompose. One day, there's a very high likelihood you're going to die. I know it's shocking, but the statistics say 1 out of 1 die. Nobody's getting off this planet alive. It's very shocking. I don't know why we're not doing more about this problem. But one day, if we die, then we're going to become food for worms, like it talks about in Shakespeare. This brings in your literature classes. And you're going to decompose. Your molecules are going to break down. You're going to be worm fodder. All right, so I want to look at the 2 ones first. And you can see here we have a nice molecule, and it broke down into 3 things. Now, for the romance, it'd be better to just think of 2. Because if we're breaking into 3, that's really weird. But, so just, think about we have one thing breaking down into 2 or more. With synthesis, 2 or more things get together into 1. Everybody got that in your head? Okay, now let's go back, and this is where you might have learned this back in biology. I always try to pull the biology back in, is when you learned about proteins. Proteins are made out of what? It's a joke. What's the opposite of a nice young base? We don't have many science jokes, so we have to use them when we have them. So the opposite of a nice young base is a mean old acid. Amino acid? Okay, it's a bad joke, but we don't have many in science, so we have to go with it. So proteins are made of amino acids. Y'all remember that from biology? Yeah. Was your teacher as silly as me and told you the joke? No. When I was talking about this last semester, Miss Raymond hopped in, she heard amino acid, and she jumped in and said, "What's the opposite of a nice young base?" It was like on cue. It was beautiful. So next year in physics, you'll get Miss Raymond and you'll get more crazy jokes. Amino acids. Okay, what are carbohydrates made out of? Sugars, simple sugars. Good job remembering your biology. And remember, these are both called monomers. Remember that? And put together, they make polymers. Remember that? We're going to be making some polymers in chemistry. We can't let biology have all the fun. All right, our third kind. Okay, sometimes getting together and breaking up is not this simple. What happens sometimes? It's more scandalous.
A court case.
What might cause that court case? An affair. An affair. So this is the affair. How do you spell affair? I don't know.
It's like
Is it 1 F or 2? That looks kind of over F'd, doesn't it?
I think it's 2 F's.
Okay, good. Okay, this is called single replacement. Okay, so notice we have happy couple, hydrochloric acid, hydrogen and chlorine. In comes zinc, and it makes eyes at chlorine, and bada bing, bada boom, zinc runs off with chlorine and poor hydrogen all by itself. It's so sad. Now, can it always happen? Are some relationships affair-proof? Yes, if it's true love. It doesn't matter how good-looking zinc is. Chlorine is going to stay true if it's true love. Like the Princess Bride, true love. Now, how do we know if it's true love or not in chemistry? Okay, how we tell it is there is something called an activity series. And I will give you one of these. And you look at it and you can tell whether a reaction will happen or not. It's sort of like, I know they had this at my old school, maybe they have it here too. The wrestling team had a strength chart. They would wrestle each other, and then there'd be some guy who was number one. He had beat everybody. And then there'd be somebody else who was number two, and someone else number three. And they would compete, and they had a chart of who was the best. So I don't know if y'all, but that's why you have a little wrestler there on the side of your paper. Okay, so think of it like a strength wrestling or a strength chart. And the strongest is on top, the weakest is on the bottom. Okay. The strongest element is on top, the weakest